Welcome back. This is an Aleks training video on predicting the relative ionization energy of elements. An ionization energy is the amount of energy you have to add to a neutral atom to rip off one of its electrons and make it into a cation. So where that electron happens to be will mean how much pull that the nucleus is having on it, and since it's a tug of war, the energy that you have to put in to rip it off will be more or less depending on how strong the nucleus is pulling on that electron. So what makes it pull stronger? It's going to pull stronger if it's closer to it. So anything that's going up is going to be increasing. It increases the amount of energy to pull it off, because if it's very, very close to the nucleus, it's holding tight, you're going to have to add more energy to pull it off. So the farther away you are from the nucleus, so farther down the periodic table towards francium, the cheaper it's going to be, because it's easier to rip off one electron from rubidium than it is to rip off one electron from lithium. Okay, lithium's closer to the nucleus. Now that's very logical that you would say it'd be closer. The other one's a little harder. That is that as it goes across the periodic table, okay, from left to right, so like let's go across sodium to argon. As you're going from sodium to magnesium to aluminum to silicon to phosphorus, you have more electrons there in the valence shell. You have 1 and then 2, and then aluminum has 3, silicon 4, phosphorus. As it goes across, that increase in electrons is going to act like a stronger magnet that's pulling on the protons that's in the nucleus. So what's happening is that more electrons you have, the tighter that the nucleus is pulling it in. So you're going to have, it's going to be harder and harder and harder, or more money to pull off an electron the closer it is to, say, the noble gas. Think of it this way: if I'm in sodium, if I am in nitrogen, and I want a configuration equal to neon, I only need 3 more. Okay, so neon is very stable. One of the stability factors is that it's being pulled in so tight. It's pulled in so tight that it's very stable. Fluorine is more stable than oxygen for that same reason. It's pulled in nice and close and snug in the bug. You're increasing in the energy required to pull it away. So when you get to the last group, it's very, very expensive to pull an electron off because it's so stable. So for that reason, anything towards the right of the periodic table is going to be more expensive. Anything towards the top of the periodic table is going to be more expensive. And then the other way would be cheaper. All right, so they're going to give you several and ask you to rank them. So let's see what we have. We have strontium. Okay. We've got magnesium. We've got beryllium. And we've got francium. And you need to put them in order of lowest to highest. I think in this example, highest is 1 and lowest is 4. Okay, highest to lowest. So highest would be the 1 and the lowest. Now, which one is most expensive? It's wherever it's increasing. Okay, that's most expensive. So beryllium is going to be the most expensive. So it's going to be 1. It'll be 1, which is the highest. And then what's the next expensive? The next most expensive is magnesium, so this would be number 2. What about the next one, strontium and francium? Which would be the next most expensive? See, francium is further down, but strontium is also further to the right. Okay, so it is only 2 below magnesium. I think strontium would be the next. So strontium would be 3, and then francium is 4, and francium's the lowest. Okay, having a picture always helps. So having a periodic table when you're doing these problems is, I would say, a necessity. Thank you.